Well, I hope you are enjoying the last lesson of the semester in Math 346. So I didn't do this last semester, and so I wanted to make sure to do it this semester. I wanted to make a video on what happens when you discretize the wave equation and then suddenly realize that you don't have everything that you actually need to solve for all of the different steps. So recall that we have a second derivative in time equals c squared times the second derivative in space, in this case x. This is the one-dimensional heat equation, 1D. And if we use the central difference derivatives for or finite difference methods for the second derivative in time and the second derivative in x, you end up with a very nice discretized equation. I'm going to write it here. So you have u I j plus 1, and I like the superscripts on the j's, at least the time indices, just pops out to me better where I can actually keep track of them. So u sub I j plus 1 equals c squared delta t squared over delta x squared. And then we have the quantity u I plus 1 j minus 2 u I j plus u I minus 1 j. And of course, these terms come from the second derivative in x, plus 2 uij minus uij minus 1. So let's just go through the thought exercise here. We know what c is. We know what delta t is. We know what delta x is. And we know every term that is in the current time step, the j time step. So we know this term, this term, this term, this term. And then we have a bit of a problem, because when j is equal to 1, you get u sub I 0. And if you were at the 0th time, you'd get -1, and this seems bad. So it appears that we actually need some information about not only the current time step, but the one before. And this is not good, because we obviously can't go back in time. Now, what we can do is we have initial conditions, so we can figure out what the displacement is at the current time. But what do we do with this j minus 1 term? This is going to pose an issue. So what else do we have? As I alluded to, we have initial conditions. So this is called Cauchy data or initial data. So what else do we have? Well, we know that the initial displacement is equal to u x0 equals 1/4 x L minus x. So it's a nice parabolic initial condition, like you grab the string as if you're going to pluck it. And then we have initial velocity. And initial velocity, u sub t, x0, equals g of x. Now, what will become very important later is that we only know this relationship in one point in time. And if you're thinking that, well, it's probably when t equals 0, you're 100% right. So we only know this relationship when t is equal to 0. And if we're thinking about this in MATLAB terms, when t is equal to 0, because MATLAB doesn't index at 0, this would actually correspond to when j is equal to 1. So we only know this information, u sub t x0, so the initial velocity, is equal to g of x only when j is equal to 1. So hold on to that thought as we move forward. So this u sub I j minus 1 term, the previous time step, is fine once you get past the second time step. Then you can actually reach back into 2. We know that we have initial data, but we basically need to have 2 time steps worth of data in order for us to actually use the loop that you used in the last lesson. So it does appear that we're going to actually have to do something different for the first time step. So we need a different approach. for the first time step only. All right. So our goal here is going to try and relate this u sub I, j minus 1. So need to relate u sub I, j minus 1 to something we know. Well, we know finite difference methods, and one thing that we haven't actually looked into is this initial velocity. Let me underline this. So it seems like we could actually use finite difference methods to get a general idea of what the first derivative is. And remember that the name of the game here is we're trying to relate this u sub I j minus 1. So the finite difference method we use needs to probably have this j minus 1 term in it. So that eliminates the forward difference. And you could probably argue that you could use the backwards difference, but typically the central difference is more accurate. So we're going to use that one. So in general, u sub t is approximately equal to, in finite difference methods, u sub I j plus 1 minus u sub I j minus 1 over 2 delta t. And again, I'll write this in here. This is a central difference. Central difference approximation for u sub t, right? But remember that we only have data. We only know something about the initial velocity at t equals 0, or this corresponds in MATLAB world to j equals 1. So what we're going to do is we're going to just pretend for one moment that j is equal to 1, and use the governing PDE, the discretized equation, and let's call this equation 1. Okay, so we're going to use equation 1 and just let j equal to 1. Now I will just be I. We're not going to just, I is the spatial value, so we'll just let I stay the same. And we're going to just go ahead and plug in j equals 1 everywhere. Okay, so for j equals 1, that means that what I have on the left side of the equation, equation 1, is u sub I, and then 1 plus 1 is 2, equals c squared delta t, squared over delta x squared. And then we have u sub I plus 1, 1 minus 2 u sub I 1 plus u I minus 1, 1 plus 2 u sub I 1 minus u sub I 0. So this u sub I 0 is the thing that we're trying to figure out what to do with, right? So continuing with this idea that, at j equals 1, we actually know some additional information, and only when j is equal to 1. We'll take this general central difference for u sub t and effectively do the same thing. So for j equals 1, that means that this derivative u sub t is equal to u sub I 2 minus u sub I 0 over 2 delta t. And what does this equal? This is approximately equal to the initial velocity, or the velocity. And when j is equal to 1, that's the initial velocity, and we know that that's equal to g of x. So this is it's not even really a trick, it's just this extra step that we have to go through for the first time step. So all we're really going to do is plug this in. So let's solve for u sub 0, because that's actually what we don't know. That's our unknown. So u sub 0, or u sub I 0, well, that's equal to, so I'm just going to multiply both sides by 2 delta t, and then you subtract u sub I 2, but then you flip the signs. So I'm just going to do this in my head. U sub I 2 minus 2 delta t g of x. Okay, so all I did was flip the sign. So hopefully this makes sense. All right, well, and now all we're going to do is take this u sub I0, and we want to stuff this back into the original equation. Okay, so just to save myself a little bit of time, which I'm sorry about, since you can't do that, I'm just going to pull this equation down here and then plug in. So be careful of the signs. It's minus u sub I 2 minus 2 delta t. Oops, that is the worst delta ever. Minus 2 delta t g of x. Okay. So this is fine. Yeah, I feel like we've made some progress here. But some of you may have already noticed that we have another problem, and it's right here. Boo. So, boo. We now have something that is the next time step in the right-hand side, which is supposed to be everything that we know. Remember, that is sort of the point or it is the point with discretized equations. We want everything we know on one side of the equation so we can solve for the thing we don't. And then we've just created another unknown, which is the next time step. So what we're going to do is just collect like terms. So we just need to bring this u sub I2 onto the left-hand side and combine it with the u sub I2 that's on the left. So I want you to pause the video here. And I want you to do the algebra. And then I will continue, just hit unpause, and I want you to just check what you've done with what I've done, and just make sure you arrived at the same answer, okay? So I'm going to take this equation that we created, just pull that to the other side. All right, so we'll just go ahead and continue on this page just so I have everything. All right, so this is actually not terribly difficult, which is a good thing. Math is not that hard. So you have a negative, and then you multiply this by the quantity. So the u sub I2 is negative, and then this, it's purple. Then this 2 delta tg of x, we just make that positive. So I just distribute the negative sign there. Okay, and then obviously it should be pretty clear that we just add u sub I2 to both sides, and then you get 2 u sub I2 on, you get two displacement values on the left side for the next time step. And then everything else on the other side is the same, so I'm going to exercise a little bit of efficiency here and copy this down. And erase that guy, and bring this over. All right. And I'm just going to pause for 1 second just to make sure I didn't make a silly algebra mistake here. Okay, I think we're good. All right, and so now the only thing we have left to do is just take this u sub I2 and or take the 2 in front of it, the coefficient, and just divide everything by 2. Now, you could put a 1/2 out front of everything, and that's fine. But just to simplify your code in the loop without having to have a bunch of extra parentheses, which can make it really hard to read, what I like to do is I like to distribute the 1/2 to every term. So you have u sub I2 is equal to, so we're just going to take the 1/2 and multiply it by every term. So the only difference with the first term here is I'll end up with a 2 in the denominator out front. So I'll just have a 2 here. And then you can see that if you multiply every single term by 1/2, we cancel the 2 coefficients out front in the next term. So it's just plus u sub I1 plus delta t times g of x. All right, so this is the equation that you need to use for the for the j equals 1 time step, right? So you have your initial data, and then what you'll do is that your first loop, if you will, or your first step is just this equation here, okay? And you'll